And now as part of the second step, what happens is the distance between each and every data point to the cluster center is calculated. So this would give you D1. Distance from this data point to this cluster is D2. Distance from this to this is D3. And distance from this to this is D4. So you have 4 distance values. Now, which distance is the least? Is this rectangle closest to this plus sign here? Yes, it is closest to the plus sign. Hence, this data point would form a cluster with this. This data point would form a cluster with this. Now, step 2. Distance between this data point to this cluster centroid, third cluster centroid, and the fourth is calculated. Now I get a sense that this black circle is close to this red triangle. So this would go and form a cluster with this because it has the least distance. In that way, distance between each and every data point to each and every 4 cluster centroids is calculated. To whichever cluster centroid a specific data point is close to, it will go and form a cluster with that. For example, this will go and form a cluster with that because it's very close to this. This will go and form a cluster with this because it's very close to this. And if you look at probably this data point, will go and form a cluster with that. In that way, clusters are generated. Okay. Now if I move on to the next, look at that. Right? All these data points formed a cluster with this. All these formed a cluster with this. All these plus signs formed a cluster with this, and all these data points formed a cluster with that. But first time when we have generated the cluster centers, it was randomly generated. So we really don't know whether that is accurate or not. So what happens is, using all these data points, a cluster center is calculated. Using all these data points, another cluster center is calculated. Using all these data points, a third cluster center is calculated, and using all these data points, fourth cluster center is calculated. These cluster centers are called as centroids. These cluster centers are called as centroids. Now, fine. You're saying that using all these data points, a cluster centroid is calculated, but can you show me hands-on on how to calculate that? Yep, we will go there. Oh, is it not here? I believe it's there in the hands-on, so let me take you all to the hands-on. Alright, so look at this. Just assume for now that we have only 5 data points. In our exercise, we have generated 50 data points with X and Y. Right? But here we have given the names as, say, V1 and V2. So we have 5 data points. And those 5 data points are plotted here. V1 is 1 and V2 is 1, so you have a 1 and a 1. So for second data point, V1 is 2 and V2 is 1, so you have a 2 and a 1. For the third data point, you have a 4 and a 5, so we have a 4 and we have a 5. And for the fourth data point, we have a 7 and a 7. In that way, we have all the 5 data points. And fifth one is 5 and 7. 5 here and 7 here. Okay. Assume that 1, 2 and 3 is part of one cluster. 4, 5 is part of another cluster. This is given a name cluster A, and this is given a name cluster B. We are saying K equal to 2. So it's 2 means clustering. 2 means clustering. K equal to 2. So now let me move on to the next slide. What shall I say is the right answer to calculate the cluster centroid? Back to our discussion. So here, if you notice this clearly, and if I take you to R and try to show this, each cluster center would have an entry on x-axis and an entry on y-axis because you have x and y. This also would have an x and a y. This also would have an x and a y. This also would have an x and a y. Okay, so x and y is required. Now if I go back to the presentation, we have 1, 2 and 3 part of A, 4 and 5 part of B. Now in order to calculate the centroid, you need to have both x and y, right? So centroid, the right answer is this. You take an average of all these three numbers, it is 7 by 3, which is 2.33. And when you take an average of all these three numbers, it is 7 by 3, which is 2.33. And when you look at cluster B, if you take an average of these two numbers, it is 6. And if you look into these two numbers, it is 7. Right? So you have two clusters, cluster A and cluster B. And we have these values. So how are they calculated? Taking the average of x and taking an average of y. If you assume that this is x and this is y, then take an average of all the x's of a cluster, you'll get the centroid values. Fine. Now, I'm going to proceed further. All right. So now there will be new cluster centroids because we have recalculated those using the data point. So if I click on next, look at that. The cluster centroids have moved. Now what happens is the distance from each and every data point to the cluster centroid is calculated. For example, distance from this data point to this centroid, this centroid, this centroid, and this centroid is calculated. And how is the distance calculated? Distance between 2 points, say this point and this will have an x and a y. This will also have an x and a y. And if you want to calculate the distance, the default is Euclidean, which is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So all the distance assumptions which we have discussed earlier in hierarchical clustering will hold true even here. Now after the distance is calculated, I believe this data point is closer to this circle, so it will form a cluster with that. Right? Now distance between this data point to cluster centroids is calculated. And I believe this data point is closer to this cluster centroid. Hence, this will go and form a cluster with this. All right, probably this data point plus sign, the distance between this and each of these 4 cluster centroids is calculated. And I believe this is closer to this, so this might go and form a cluster with this. So based on the least distance, the data points get assigned to different cluster centroids. Well, let's see what happens here. Look at that. So this is how the cluster centroids are formed now. Once again, we don't know whether this is the best cluster. So using all these data points, all these black circles, a cluster centroid is calculated. Using all these data points, another cluster centroid is calculated. Using all these, third one, and using all these, fourth cluster centroid. Once again, there will be a movement in the cluster centroids. Once again, distance between each and every data point to each and every cluster centroid is calculated. And whichever data point is closer to a centroid, it will go and form a cluster with that. And this process would go on and on and on and on until there is no further movement. Oh, yep. Now there is no further movement. What does that mean? if you calculate the cluster centroid using these data points, it will remain the same, it will not change. And if you calculate the cluster centroid using these data points, it will remain the same, it will not change. And if you calculate the cluster centroid using these data points, it will not change and it will remain the same. And this is what is clustering. And this is how your k-means clustering would determine what is the best cluster. And your clustering exercise is considered to be complete if you can properly label these clusters. I'll show you a case study post discussing about the rest of the components of k-means clustering. Okay. So if I were to explain you all on what is there in this KM1, I would just do KM1 or structure of KM1. It will give me all these values, right? But if I look into this, if I do not do with animation.ani, and if I look at structure of KM, it would give me slightly more values. Because this animation, it was truncated. Here you have all the values. So now let us look at this and try to understand. The first part here is $cluster. So if you want to look at all the values of this $cluster, all you need to do is do a KM $cluster. There we go. So the first data point in your data set, in this data, the first data point belongs to first cluster, second first cluster, third first cluster, fourth one belongs to the first cluster, fifth data point belongs to third cluster, sixth data point belongs to second cluster, so on and so forth. That's this. Now if you look at the centers, how many centers do we have? If you want 4 clusters, you'll have 4 centers. So if you do KM $centers, you'd be able to see X and Y for each and every cluster. As I've told you, each and every cluster center or centroid would have X and Y. All right. Now, what is this within sum of square? If you notice, you have 4 values of within sum of square. How is it calculated? Distance of each data point from the centroid, you'll get 1 value, and then you add it with the distance of this, this. So from each data point, you try to find out the distance from the cluster center. And simply take an addition, you get this value. If you calculate in that way for this cluster, the distance between each data point to cluster centroid, once again, if you add all of that, you would get the second value. For the third cluster, you have the third value. And for the fourth cluster, you have the fourth value. And when you tend to add all of those values, you get total within sum of square. If I add all those values, I'll get total within sum of square. And within sum of square should always be less. That means within each cluster, the distance should be very less. Within the second cluster, there should be a lot of homogeneity. That means there should be a lot of similarity. Distance should be less. And so is the case for all the clusters, all these 4 clusters. Now, that's within sum of squares. So the less the better. And if you try to run k-means clustering using 5 clusters, for example, and then if you want to know whether 4 clusters is better or 5 clusters is better, you need to compare those 2 models. Say you have come up with one k-means clustering with 4 clusters, and say you have come up with a second cluster and this has 5. So you look at the within sum of square, total within sum of square for cluster A. say it's 1.9, and say the total within sum of square for cluster B happens to be 1.2. This one is better. Less the better, because it means that there is a lot of similarity, a lot of homogeneity within the data set. Now, what do you mean by between sum of square? So if you try to calculate the distance between different centroids, or how do you calculate the distance between two clusters? If it's a single linkage, then you look at the nearest values. Complete linkage, the furthest values in that way. Here, we look into the distance between this centroid to this, this to this, this to this, this to this. In that way, you calculate the distance between different centroids, and when you add those, you get between sum of square. And this value, larger the better. And say you're coming up with cluster A with 4 clusters, B with 5 clusters, and say between sum of square for cluster A is 6.42, and between sum of square for cluster B is 7.8. That means this is better, larger the better. But there can be scenarios wherein within sum of square is better for cluster A, between sum of square is better for cluster B. Then probably you need to look into each clusters within sum of square and then take a call. All right. And if you add the between sum of square and total within sum of square, you'll get total sum of square. We have discussed these things when we discussed ANOVA. So I will request you to go back to that tutorial and look into this once again, within sum of square, between sum of square, and all that, to get better understanding. Now, this says that in cluster 1 you have 10 entries, cluster B you have 19 entries, cluster C has 17 entries, and cluster D has 4 entries. And this brings us to the end of the discussion of the output of k-means clustering. And as part of the next discussion, we will discuss about how to determine the number of clusters using some logic. Yep, and then we will try to do this case study using university's dataset. All right, so to determine the k value, there's a crude way to determine square root of n by 2, number of data points divided by 2. But there is a better way to calculate that, and the better way is as follows.